And welcome everybody here to this webinar. Last time I've checked, or I'm checking right now, we have over 50 people online, which is really great. Welcome. Thank you for your interest in the presentation. Before we start, when I look around me, what I see is actually I see my living room. So I'm talking to you from my living room right now, which is completely unusual because typically at an ION, when I give a talk at ION, there's a conference around it, and I see everybody, I can talk to everybody. So admittedly, this makes me very nervous because everything is different because of the very different circumstances everywhere on the world. So since we're in this very special situation, everybody is working from home, everyone is using all the different video conferencing tool. The internet is pretty much loaded, so please bear with us in case we have a technical issue. If the presentation should freeze or if you should stop hearing me, we will fix it as soon as possible and then continue and let you know, but please be patient and hang on. As Rick already said, you have the option to actually type questions into the presentation tool. There is an option to type them in. I will look at this at the very end of the presentation and read your questions in chronological order so everybody can hear them, and then I will answer them. So if you have a question, please refer to the slide number. They will be shown on the top left of the slides, and then type your question as clearly as possible, and please make them easy so I can answer them. We will not be able to actually talk to each other like we would be at a regular conference, but okay, this is a webinar, so everything is a little bit different. So that's enough. Let's get started with the actual presentation. It is on flight results of the GPS-based attitude experiment on the Canadian CASSIOPE satellites. And I'd like to acknowledge my co-authors for the presentation, and they are Oliver Montenbruck, who is, like me, working at the German Aerospace Center, DLR. We both are at the German Space Operations Center close to Munich. And then Richard Langley from the University of New Brunswick in Fredericton, Canada. Then I want to start with acknowledgements to two individuals in particular. They are Andrew Howard from the University of Calgary and Christian Siemes from ESA. They have actually, in response to our analysis, looked again into the star sensor data of the CASSIOPE satellite, and especially Christian has made a great deal of effort to provide us with a very high resolution and high accuracy star sensor data reference for our analysis, and this is greatly appreciated. So let's look at the agenda for tonight. Well, where I am, it is evening. So for this webinar, I will start talking about the CASSIOPE satellite. I will first introduce the satellite mission and then elaborate a bit on the GAP experiment itself. We will then have a look at the attitude determination algorithm that we have used to make this analysis. We will talk a little bit about mitigation of typical errors which we have, and they will be related to phase center offset errors and phase center variation errors. Then I will present some test cases, two test cases where the satellite is actually performing attitude maneuvers. We will look at the accuracy with respect to the star sensor attitude that we are getting with our GPS-based attitude determination. And then we also want to look at the time to first fix from the initialization of the Kalman filter to the first time we can fix the ambiguities. And finally, I'll finish with the summary and conclusions. Good. So let's have a look at the CASSIOPE satellite mission itself. CASSIOPE is an abbreviation, and it stands for Cascade, Small Sat, and Ionospheric Polar Explorer. And it is a small satellite by the Canadian Space Agency. However, small satellite, don't let this fool you, it's actually quite a big satellite. It has a mass of 500 kilograms, a diameter of 1.8 meters and a height of 1.4 meters. So still small for a satellite, but not so small by maybe human dimensions. It was launched in end of September 2013 into a polar orbit with it's an eccentric orbit. So it has an apogee of 1,300 kilometers approximately, and a perigee of 328 kilometers. The mission objectives are twofold. So it has commercial and scientific payloads. It is also a technology demonstrator for the satellite platform itself. The main payloads are called Cascade. This is the commercial part of the payload, and it is a terminal used for space-based file transfer. The scientific payload part is called EPOP, and it is a collection of scientific instruments, which we will look at in a minute. And Cassiope is known by many names. Since February 2018, it is part of ESA's Swarm mission, and it is called also Swarm-E now. As you may know, ESA's Swarm mission already consists of 3 satellites, 3 identical ones, and now Cassiope is the 4th one. So let's have a look at the scientific part of Cassiope, of the Cassiope payload. EPOP stands for Enhanced Polar Outflow Probe, and it is a payload consisting of 8 instruments for space weather research. You can see the list of these experiments on the left side. I'm not going to go through all of them, but here you see the GAP experiment, which is again an abbreviation, of course, for GPS attitude, positioning, and profiling experiment. On the right-hand side, you can see a drawing of the satellite, and we will go into the details, but you can see the placement of the various experiment. You can also see the antennas on the top of the satellite. Let's look at this a little closer. So let's look now at the GAP experiment in particular. It was developed at the University of New Brunswick in Canada, together with several other partners. The University of Calgary, McDonald Detweiler and Associates, as well as Bristol Aerospace. And it consists mainly of 5 NovAtel OEM4 receivers. And it has 4 patch antennas on the zenith phase. So this is the part of the satellite that nominally points upwards, away from the Earth. Of course, away from the Earth, it should point towards the GPS constellation. You can see these 4 satellites on the figure on the right. I'm actually moving the mouse pointer over there. I hope you can all see this. Rick, could you please confirm real quick that you see the mouse pointer on the...
Yes, we can see that.
Okay, perfect. So you can see the 4 different antennas here on the sides of the zenith honeycomb structure of the satellite. They are small patch antennas, and there's a 5th antenna that is located on the anti-velocity direction. So you must imagine that the satellite is flying into your screen, and we're looking at the back side of it. And here, down here, where it says GPS 4, this is an occultation antenna, which is different from the others. So we will have a look at this on the next slide. But before we go there, I want to point out that we can form different baselines, different baseline vectors between these 4 patch antennas on the top, and they have different baseline lengths, typically 1 meter, so 1.05 meters and 1.13 meters, depending on which antennas we choose. And then, of course, I know I mentioned this already, we have a very precise reference attitude for our experiment because there are also star cameras mounted on each side of the Cassiope satellites. You actually see the protection baffles that protect the camera heads themselves from direct sunlight on the left and on the right. Good. So let's have a closer look at the hardware that is used in the gap experiment. As I already said, we have 5 receivers, each connected to one antenna. To make it simple, and these receivers are manufactured by NovAtel. They are called OEM4-G2L. They are dual frequency GPS receivers providing measurements on the L1 of the L1 CA code signal and the L2 PY code signal. They support different output data rates from 1 Hz to 100 Hz. Of course, the very high rate data output is relevant for the occultation measurements. The receivers have been space qualified by DLR and Bristol Aerospace, and they also have flight heritage. They are it is also flown on the CANX 2 satellite. Here on the right. Now let's look at the antennas. The 4 patch antennas are sensor system antennas. They are depicted here on the right side. The smaller antennas are the sensor system antennas. They are mounted, as I already said, on the zenith face of the satellite, and they're used for precise orbit determination and attitude determination of CASSIOPE. Then we have one special antenna for radio occultation measurements. This is a NovAtel GPS 702 pinwheel antenna, and it is depicted here. It's the larger antenna in this figure. And those who know the NovAtel pinwheel, it does not really look like it because it has been rehoused. So the original housing has been removed and it has been put into a, say, space-suitable housing here. Then there are also spectrum microwave LNAs built into this experiment to connect the antennas to the receivers. Before we go on, I'd like to mention that due to memory restrictions on board of the satellite, the gap experiment is not activated all the time. So not all receivers are active all the time. And typically one receiver is active because orbit determination of the satellite is necessary all the time. But for dedicated attitude experiments, up to 3 or 4 receivers can be activated. Typically, we have 3 receivers active for, let's say, time periods between 10 and 100 minutes. These activation times are relatively frequently, though, but as I said, we don't get it. We don't get data continuously. The same is also true, of course, for the ionospheric occultation measurements, where you have the very high data rate, and they are really only activated for the ionospheric measurements at dedicated experiment times. We are, however, only using the patch antennas on the satellite, on the top of the satellite. We're not using any data from the occultation receiver. Okay, let's have a closer look at the antenna mounting, because it's very relevant later on. What you see in this figure is the zenith honeycomb structure of the satellite. You see it has a large solar array to create energy for the satellite. And you can see on the sides here the patch antenna with the red dot in the middle. So here are the 4 antennas. And you can already see that there's a difference in how the antennas are mounted. So if you look at the top 2 antennas, you can see that the mounting bracket, which actually holds the receiver, holds the antenna, is integrated into the panel. So there's a part of the honeycomb structure is cut out, and the antenna bracket is put in there. On the bottom 2 antennas on the slide, we see that the bracket actually points outwards, and it's referred to here as an external bracket. And this already gives us an indication that there is maybe some effects to be expected from the different mounting orientation and from the different mounting or from just the physical properties of the different mounting. Good. Now let's start talking about the attitude determination algorithm that we're actually using. So the algorithm is based on the Kalman filter, and as a matter of fact, it is the algorithm which I have implemented during my diploma thesis almost 14 years ago when I joined DLR. The state vector in the Kalman filter consists of the baseline vectors. In our analysis, we usually have used 3 receivers, so we can form 2 baselines. Every baseline vector has 3 components, of course. Then we have an angular velocity vector, which is commonly estimated for both baselines. Also, this angular velocity vector has 3 elements. Then we have the differential receiver clock offset between the 2 receiver pairs. There we have 1 per baseline. And finally, of course, we have single difference carrier phase ambiguities, n per frequency and baseline, where n is the number of satellites that are being tracked. We process single difference carrier phases and pseudo ranges, and we can process L1 only, L2 only, or dual frequency measurements with this algorithm. The ambiguities are estimated as single frequency ambiguities, so they are separate for each frequency, even if we process dual frequency measurements. And we can resolve the ambiguities by forming double differences of ambiguities, and we resolve them with the M lambda method. Then, since we are actually estimating baseline vectors rather than an attitude directly, we retrieve the attitude solution using the quest method or the triad method. So these 2 methods are used for converting measured baseline vectors and converting the information from measured baseline vectors in one reference frame and a set of known reference baseline vectors in different reference frame into an attitude orientation between these 2 reference frames. So we are actually measuring or observing through GPS the baseline vectors in the ECEF frame. We know them from the mounting positions in the satellite frame, and thus with the quest method or the triad method, we have the attitude then from the ECEF frame into the satellite body fixed frame. Now, we also know the orientation of the Earth with respect to the inertial frame. So by putting these 2 transformations together, we can finally arrive at the orientation of the satellite body frame with respect to the inertial frame. And we get the same information from the star sensor cameras, but directly. On the right-hand side, you can actually see a flowchart of the Kalman filter and the algorithms around it. So let's walk through this real quick. We jump in on the top right with the initialization of the Kalman filter. So this is where we set initial values for the state vector elements and also the state vector covariance. Then this is done at the very beginning when the Kalman filter is started for the first time or restarted after a long data gap. Then we go through a data quality control where we screen out corrupted data. We detect cycle slips through a triple difference, so time differences of double differences, which helps us to screen out all the cycle slips. We also make some basic checks like C over N0 limit. If the C over N0 is too low, we reject the measurements. Then we have elevation angle-based thresholds and so on, which help us to clean the data. Then in the next step, we have the Kalman filter measurement update. where we process our carrier phase and pseudo-range measurements. Then we check if we have float ambiguities, so ambiguities which have not yet been fixed in the Kalman filter state. If this is the case, we form, as I already said, double difference ambiguities and try to fix them with the M-lambda method. Then the ambiguities are validated. I'm going to talk about this in a little more detail on the next slide. If we can successfully validate the ambiguities, we fix the ambiguities in the filter with a pseudo measurement update, and then jump back to the main part of the algorithm, where we use the triad or the crest method to convert baseline vectors into attitude. This is the output information, or one of the output information of the filter. And then we go to the Kalman filter state propagation phase, where we're actually propagating this state to the next epoch, which is typically 1 second away, because we're getting 1 Hertz data from our receivers. And then the loop starts over again with the data quality control for the measurements of the next epoch. Okay. Of course, if we do not have any float ambiguities in the Kalman filter state, we jump directly to the triad and crest conversion of the attitude. Good. Let's have a closer look how the Kalman filter state is actually propagated. So I've already said we are assuming one constant angular, we assume one common angular velocity vector for all baseline vectors. And in our model, we assume that the angular velocity is constant. Not zero, but constant. However, this is of course not true, because when the satellite performs attitude maneuvers, we have to add some process noise, or we are actually adding process noise all the time to the angular velocity state to account for rotations of the satellite. So when the satellite changes its orientation due to a reorientation of a camera, for example, or if it wants to keep contact with a ground station for data transmission, then the angular velocity changes, and this is compensated for by the process noise. The baseline vectors are rotated in the prediction step based on the velocity, on the estimated velocity vector. So we assume that from one time step to the next, the satellite keeps rotating based on the previous velocity vector, and there is no additional process noise added to the baselines. We assume a white noise model for the differential receiver clock offsets, and we assume constant carrier phase ambiguity. Good. So let's talk a little bit about ambiguity validation. Of course, just fixing the ambiguities is not enough. We also have to make sure that we're fixing to the correct ambiguity values. What we do here is, since we know the baseline length from the drawings of the satellite or from the calibrations that we have done previously, what we can do, we can compute a baseline vector with using the ambiguity integer candidates that we have retrieved from the M-lambda method. So we use these carrier phase, the corresponding carrier phase measurements to compute a baseline vector. Then we test the baseline vector length with respect to the expected length that we know, and we assume that the integer candidates are correct if the difference between the computed baseline length and the expected length is below a certain threshold. And we found out that this is a pretty good acceptance test that prevents us from including incorrectly fixed ambiguities in the solution. So let's actually look at some results now. So here we see results for a satellite pitch maneuver on June 6, 2018. So the data set is about like 20 minutes long, a little bit longer. And you can see on the on the left side, you can see the Euler angle errors, which are the errors in your pitch and roll error from the GPS-based editor determination. And these are the red, green, and blue dots that you see here. On the right-hand side, you see the actual Euler angle orientation from the reference attitude, and this refers to the solid line here. So we see that the satellite, in reality, starts with the orbit normal orientation, how we call it. So the three Euler angles are 0. And then here in about the middle of the data set, it starts a pitch motion. Green is the pitch angle. That goes up to about 55 degrees, and then rapidly goes up, and then slowly goes down until to minus 40 degrees approximately. And there's not much change in yaw and roll. Okay, but let's not look at this for now. Let's really look at the Euler angle errors here. So the first thing that we see is that they are biased. So we have a yaw bias of minus 0.57 degree, a pitch bias of almost 0.2 degrees, and a roll bias, which is largest of minus 0.7 degrees. So we have biases, and we also have noise, but we also have a systematic variation. So if you look at the blue line here, the roll angle, you see how this varies over time systematically. So clearly there's more in the data than just noise. And we already have a clue what this could be from previous experiments. We need to calibrate the real flight data to correct for two different errors that are the main error contribution here for the systematic measurements. The first problem that we have is that we know the mounting positions of the antenna to probably a sub-millimeter accuracy based on the technical drawings. However, we do not exactly know the true electrical phase center of the antenna. And you know this problem very well from geodetic positioning, where the physical antenna middle point, so to say, or center, does not necessarily coincide with the electrical phase center of the antenna. So, for example, you may know the antex corrections that are available for the antenna phase centers. So this is one problem. The electrical baseline length, if I like to call it like this, or the difference between the two electrical phase centers of the antenna is not necessarily identical with the geometrical difference of the phase centers. So this is one point. The second point is the variation of the phase center depending on the elevation angle and the azimuth angle with respect to the antenna frame. And this can be caused by different things. Firstly, if you take one isolated antenna, and even the very geodetic high precision antennas, they are also prone to this problem and to this variation, that simply due to the structure of the antenna and the design of the receiving elements in the antenna, there is a variation depending on the elevation angle and the azimuth. And again, in the geodetic processing world, you have correction values for this. Now, if we have these integrated patch antennas on a metal structure on a satellite, we have the problem that this metal structure of the satellite affects the electrical phase center offset, but also these elevation and azimuth angle dependent variations. And this will even be more pronounced differentially between two antennas if these two antennas do not have the exact same, let's say, mounting vicinity around them. And we've seen at the very beginning of the slides that these two antennas have different mounting geometry,
on the satellite. So it is not surprising that we will have this effect very pronounced with these patch antennas. So what can we do about it? The first part, so the difference of the phase centers, can really only be corrected using a precise attitude reference. And because in the end what we have to do is we have to correct our geometric baseline vector length with the measurements that we actually see. And we can do this by computing the baseline vectors at each epoch, preferably during many data sets, and ideally during data sets during which the satellite is not doing any crazy rotations, but ideally it is in orbit normal orientation. And then we can compare our estimated baseline vectors with the expected baseline vectors based on the reference data. So we're actually using the star sensor reference data here. And then we can average over all the data sets that we have, and we can come up with a correction. The second correction is a correction for the variation based on elevation and azimuth, and there we do the same thing. So we use our averaged corrected baseline vectors from the first step of the procedure, put them in, and then compute residuals based on elevation and azimuth for the carrier phase measurements. And then we average these residuals and produce a map. And I will show the result on the next slide. However, we have a problem here because we have two different frequencies. We have the L1 frequency and the L2 frequency, and it can be expected that the phase center offsets and the elevation and azimuth dependent variations differ for the different frequencies. So what we do here, we kind of go a compromise. We do a compromise here. We compute one mean baseline vector based on the L1 and the L2 observations together. So one baseline vector, and then we compute the phase center variation, the phase variation corrections for L1 and L2 separately, and this also includes the difference between the L1 and the L2 phase center offsets. Then I apologize, there is a typo on the slide, so this should be the L1 and L2 phase center, of course. Good. Let's look at results. So, slide 13. Slide 13 shows the phase center variation maps for the GPS L1CA observations. And we have one map for each antenna pair. So on the left side we have GPS 1, 2, and on the right side we have GPS 0, 2. And we can see that the variation is quite large, from -25 to +25 millimeter peak to peak. Let's look at the next slide. I'm switching now to slide 14. And this shows the same result for the GPS L2 frequency. Same antenna pairs, and we can see that the peak-to-peak amplitude variation is even a bit more pronounced, I would say, compared to L1. So if you look at the dark blue here, or if you look at the dark red or white areas here, and if I jump back to slide 13, and then forward again to slide 14, you can actually see that it is even a bit larger. So let's compare on slide 15 now. For the same antenna pair, the L1 and L2 phase center variation maps, and we can see that they are quite dissimilar. So we actually need separate calibration for both frequencies, And of course, mind what I just said before. This is not purely only the elevation and azimuth dependent variation, but this is also accounts for the difference in the actual phase center offset difference between the L1 and L2 frequency. Yeah, so we have two effects here in the same map. And I think I also said, let me repeat this as well and go back one slide. We have a very dissimilar phase center variation map for both antenna pairs. And of course, this is expected based on the different mounting geometry of the patch antennas on the satellite. Okay, so let's go back to our attitude determination results. I'm on slide 16 now. And you have already seen this slide. It was the one that I presented before. We have the biases and we have the systematic variations in it when we are not applying any calibrations. When we apply the calibrations that we've just derived, then the situation changes to this. So you see the biases are mostly gone. So if you look at the yaw angle offset, it has gone down from more than half a degree to 0.14 degree, and the pitch angle is even smaller, and the roll angle is on a similar magnitude in terms of the biases. So this is, of course, due to the baseline vector calibration with flight data. We also see that the systematic variations have been reduced significantly, not totally as we will see, but very much. So especially in yaw, we have a 0.025 degree standard deviation here, when we had before more than double of that. And the same is also true for pitch and roll. The standard deviation has been reduced by about 50%. It is interesting to note, if we're looking, I believe, on the next slide, if you look at the same figure again and look a bit more on what the satellite is actually doing in the background, so you see that it's most of the time in orbit normal orientation, and then it starts a pitch motion in the one direction, it reverts, and it slowly goes back pitching into the other direction. So this could, I'm not sure what it actually was, but I assume it may have been a ground station contact where the antennas on the bottom side of the satellites are pointed towards towards the ground station that comes up front of the satellite, and then it flies over the ground station, and then the ground station is behind it. I'm just assuming that, but this would be a typical scenario for such a maneuver. What we can actually see, if you look at the green dots here, the pitch angle errors in the middle of the data set, where the pitch motion starts. So I'm circling this with a yellow circle now, and you can see that there is a bias of a -1 degree in the Euler angle error that coincides with the point in time when the pitch when the pitch rate is really large. And the problem that we see here in this rapid pitch motion is that the process noise that we're actually applying to our velocity vector, angular velocity vector, is in this particular situation not large enough. So the yaw angle and the angular velocity vector is not updated as quickly as it would be necessary in this situation. And this results in the pitch orientation of the satellite lagging behind, or the estimates of the pitch orientation lagging behind the true orientation. Now we have a very easy mitigation against this. This would be to increase the process noise on the angular velocity vector. But then again, we are, of course, reducing actually the impact of the Kalman filter, and we would get more noise on our estimates. So as a trade-off, we're doing well with the value that we have selected most of the time, but we see the limitations on the very rapid pitch motion of the satellite. Good, let's look at a different example for an attitude maneuver. This is a yaw maneuver. So let's look at the solid lines first. We see that we have yaw, pitch, and roll here at certain values, more or less close to zero at the beginning. And then we see that the red line, the yaw angle, actually approaches minus 180 degrees. So the satellite is turning around by minus 180 degrees. And we also see a 90-degree roll and a minus 30-degree pitch here. So it's a rather it's quite a deviation from the orbit normal orientation of the satellite. What we can see that the yaw, pitch, and roll errors are still similar to what we've seen before. So the biases are on the order of 0.1 degrees, and the standard deviation is on the order of 0.2 degrees, very similar to the previous example. And so this is one example, but the results are quite typical for what we're actually getting with GPS-based dual frequency attitude determination when we apply all the calibrations using flight data. Okay, then let's look into something that is very interesting, and we are approaching the end of the presentation. We want to look at time to first fix. So how fast can we actually get a high precision attitude estimation with resolved ambiguities after starting the Kalman filter? And to assess this, we have selected 20 different test cases with what we call lost in space orientation. So this is one example for them. Again, if you look at yaw, pitch, and roll errors, we see that this data set starts with a pitch orientation of almost 50 degrees, and yaw and roll less than 10 degrees, but it then approaches zero for all three yaw angles, so orbit normal orientation. And the test is we start here and we check how quickly, how many epochs we need to fix all ambiguities on both baselines for the first time. And we do this test for the L1, the L2, and the L1 and L2 frequency. So 3 different tests. Here are the results for the time to first fix analysis with these 20 different test cases. Again, our test criterion is that all ambiguities are fixed on a baseline. And I'm sorry, we're doing it for both baselines separately. I remembered this incorrectly. On the right side in the table, you can see the 20 test cases, and you can see the initial attitude of these test cases. And then you see the three columns to the right, where we're using L1 and L2 measurements, L1 only, L2 only, and you see the time to first fix for the 2 different baselines. And you see that it's mostly, if you look at the L1 and L2 time to first fix, it's mostly 0, except for a few exceptions. And then if you look at L1 and L2 separately, you see, okay, sometimes we need much longer, but quite often we still have immediate fix of ambiguities. In a graph, we can see it actually here. Blue is the one baseline, red is the other baseline. We see that for L1 only, on average, we need between 8 and 10 seconds for the time. Oh, sorry, between around 8 and 9 seconds for the time to first fix. Then this improves when we're using L2 only. Yes, around 5 seconds time to first fix, and it dramatically improves if we're using the dual frequency measurements. This is, of course, an expected result. The L2 frequency has a longer wavelength compared to L1, 24 centimeters for L2, 19 centimeters for L1. So a better performance for L2 only is expected. And then, of course, if we are using both frequency at the same time, we have the best performance. Let's look at a different test here in this, or let's look at a different figure. This is the number of instant fixes, so 0 time to first fix, for the different baselines and frequencies. So on L2 only, we have approximately half of the time an instant fix. 20 test cases, in around 10 or 12 of them we have instant fixes for L1. This gets better for when we're using L2 only, but interestingly only really for one baseline. The other baseline is still similar. And of course, if we're using both frequencies, we're getting a very high number of instant fixes. Good. So this is the end of the presentation, or almost the end. In summary, we have looked at GPS determination results for CASSIOPE with the GAP payload. To our knowledge, this is the first time ever that a dual frequency data from a satellite has been used. If you know differently, please mention it in the comments, as the people on YouTube say. We have seen that we need to calibrate to get rid of the biases and the systematic variations in the data. If we apply the calibrations, we have biases of less than 0.5 degrees and a standard deviation noise of less than 0.25 degrees. And the time to first fix with dual frequency data was almost instantly in most of the cases, and we've seen that using the L2 frequency only is better than using the L2 frequency only. Okay, on my last slide, I would like to point you to some further reading on that topic. Some of the original publications related to CASSIOPE. The first one is our navigation paper on the same topic, and I believe since this is going to be recorded, you can actually review the slide and look for these presentations. Okay, with this, I have reached the end of my slides, and I would now like to go through the questions. We have a few questions in the list. Unless, Rick, there is anything else on the agenda that we should do?
No, I think it'd be great if you went through the questions. Thanks.
Good. So we have the following questions, and this is your last chance to put them in if you want to ask them. So the first question by someone is, it's actually more a remark that the speaker is not seen. Believe me, be grateful that I'm not being able to see because you can't get a haircut in Germany since about 6 weeks or so. So I'm quite glad that the webcam is not on. And the next question is that the next question is, what is the brand of the GPS patch antennas? And that was there are sensor system patch antennas off the shelf. The third question is, have you logged data at 100 Hertz? From how many receivers? How long? How you managed the large data set? Okay, to make it short, we did not. Well, we did not use it. It was logged for sure by the occultation part of the experiment, but we have not used, and it's very clear that on board a satellite you don't have infinite data storage opportunities. So the occultations really only last for a couple of minutes, and the occultation part with the high rate data is really then only on for this couple of minutes. Okay, next one. Is there any information on how to model the unknowns in the state vector? What kind of assumptions are used? Are the model settings fixed or dynamic? I'm not 100% sure if I understand the question. The unknowns are really estimated. Yeah, so the unknowns are the ones that I mentioned: baseline vectors, angular velocity vector, differential clock offsets, and ambiguities, and they are not modeled, they are estimated. I have mentioned maybe this is meant by the question, the assumptions behind the state vector elements were that the baseline vectors are constant, and they are assumed to be to rotate based on the estimated angular velocity. There's no process noise on the baseline vectors. There was process noise on the angular velocity vector, of course, to account for reorientations or attitude maneuvers of the satellite, and white noise for the clock and constant for the ambiguity. The model, the settings, the process noise settings were fixed. So we always used the same process noise settings for all experiments. I'm going to the next question. What is the baseline length measurement accuracy achieved during the GAP experiment? The baseline length itself is So baseline length is relevant for our baseline acceptance test. So we're choosing a threshold that is large enough to actually accept the correct ambiguities and not reject a correctly estimated baseline. And of course, due to the noise and some residual effects in the measurements, we have a certain noise on the baseline length. So let me answer the question in this way. We have a threshold, a rather relaxed threshold of 3 centimeters in the ambiguity acceptance test, and we have noticed, or we found out, that this overbounds very well the noise in the baseline length. Typically, the accuracy of the baseline is much lower than that, and I would say it's probably less than a centimeter. I would have to actually work out the math and convert the attitude errors back into baseline length error, but I'm not doing this out of my head right now. So let's go on to the next question. I can come back to you on that question later. What is the threshold for the baseline length in the ambiguity validation step? That I just said, that's 3 centimeters. Is the attitude divination mentioned in slide 11 based on L1 or L2 or dual frequency? Slide 11 is most likely dual frequency. Yes, this is dual frequency. These were the uncalibrated results, and these were the calibrated results on slide 17, which I'm showing right now with dual frequency measurements. Then, okay, someone noted that the slides are broken. Thank you very much for this. Next question, what would be the impact of obtaining measurements, say at 10 Hertz, from 4 GPS receivers, using them for attitude determination? It's difficult to answer that question. 4 receivers means you could form 3 different baselines, so that give you more redundancy in the measurements? And actually, this is a good question from that perspective. If we look again at these results, I'm on slide 17, and I hope you can actually see it. And if we look at the standard deviation of these measurements, you can see that it's smallest for the yaw angle, and it is largest for pitch and roll, or larger for pitch and roll. The reason for this is that both baselines, if we look again at how they are mounted on the satellite, if we're looking again at the geometry of the satellite, we know, or we recognize, that both baselines are actually contributing to the yaw orientation, which would be around this axis, pointing vertically here. So both baselines contribute to the yaw angle estimate, while only one baseline always estimates to the pitch and roll accuracy, or estimate. Yeah, and for that reason, we have a higher or a lower standard deviation in the yaw direction and a higher one in pitch and roll. If you had more receivers, like it is asked here, so if we have 4 receivers, we have 3 baselines, so you would also have redundant information on the pitch and roll axis, depending on how the baselines are oriented, of course. But so I would expect an improvement in the standard deviation of all yaw angles, but also in pitch and roll. The 10 Hertz data rate is, of course, helpful for quality editing, I would say, of the measurements. So if you have high rate measurements, the data editing can be helpful, but I would say it's not necessarily in this case, because we did it with 1 Hertz measurement and it worked very well. Next question. Did you have many cycle slips to fix? How did you handle data editing? There were cycle slips in the data, yes. We did the cycle slip editing mainly by computing triple differences, and here we connect to the previous question. So we computed triple differences, which are time differences of double differences. So that cancels out a lot of the errors, for example, the differential receiver clocks, which we don't want to have in there through the double differencing, and through the triple differencing you also actually kick out all the constant terms, like the ambiguity itself. And if the ambiguity changes, then you see a jump in the triple difference. And that was our main tool for detecting cycle slips. And this gets increasingly complicated if the data rate is lower. So 1 Hertz worked fine. We had, on a different satellite, we had an experiment where we only had every 10 seconds a measurement, I believe it was. And there we had to relax the criterion a little bit and sometimes didn't catch all the cycle slips. Good. Next question. I would like to know if the phase center variation result is calculated or measured, and what is the result for phase center offset? I only find the phase center variation results. Yes, both results were calibrated with real flight data. In the presentation, I'm only showing the result for the phase center variation map, but in the paper, in the corresponding paper, you will also find the results for the phase center offset. Okay. What is the difference in mounting for the zenith patch antennas? Was the difference in mounting for the zenith patch antennas by choice or determined by other factors? Honestly, I do not know. I would assume that it was due to engineering constraints of the satellite, potentially due to the fact that there were solar arrays mounted on the zenith face of the satellite. But to be very honest, I could not answer that question. I would recommend that you send an email to me or to Richard Langley, and we get back to you with a more educated answer. The next question, in the paper you include differential clock offsets. Is a common clock offset between receivers feasible for eliminating those unknowns? No. All receivers have their individual clocks. So a pair of receivers has one differential clock offset while the other pair of receivers has a different one. So you cannot use just one for all three receivers. Do you know or have a guess how many satellites are in orbit with 4 GNSS antennas on board for attitude determination? I do not. No, I would have to guess, and I don't. No, I can't. But it's one thing if the satellite is, if there are such experiments on orbit. It's another thing to get the data from them. So we were very lucky that this data was available to us, and we were very grateful, especially to Richard Langley, for supporting us on that. If we assume a different size for the platform, would the length of the baseline between the receivers have any influence? Yes, it does. The longer the baseline, the better, the higher the precision of your estimate. So if you assume what you're actually computing is a differential position between two antennas, yeah, and the noise as a first approximation is always identical, irrespective of the baseline length. It is mainly driven by your antennas, by the vicinity, things like multipath around the antennas, and the noise of your carrier phase measurements. But if you assume that this is constant, no matter how far you place the antennas apart, then the error in the yaw angle, or in the angle or angles that are derived from this baseline vector get smaller the longer the baseline is. Okay, we have a comment from Oliver here, which I want to read out. A comment on baseline estimation accuracy. Depending on the component, vertical DOP is worse than horizontal DOP. Kinematic baseline estimates of gap have an accuracy of about 5 to 50 millimeters without calibration of phase variations, and roughly half those values after calibration of phase patterns. Thank you. That was in response to an earlier question. We have a follow-on question to build on the previous question on the 10 Hertz. Would a high rate have an influence on the Kalman filter model settings? Not necessarily. No, I wouldn't think so. I would believe that the same or similar settings would work irrespective of the data rate. There may be other effects, though, that one might have to relax, or one could make certain quality control limits tighter or wider, depending on the data rate. Last question, does the float ambiguity degrade the accuracy of the attitude estimates? Yes, it does. So if we cannot fix the estimates, we have a significantly reduced accuracy. I cannot say a number at this point, but the GPS-based attitude determination is really only a competitor to, say, a star camera-based solution or sun sensors if we fix the ambiguities. Good. This was the last question in the list. With this is the end of the seminar, and I many thanks to everybody who has tuned in. It was a great pleasure for me to do this, and I'm handing back over to Rick, and I thank the ION very much for giving us the opportunity to present our work.
Well, thank you, Andre, for your time and for your thoroughness in presenting, preparing, and answering all of these questions. We thank you so much. And we remind those of you who are viewing that we will have an archive of this broadcast on our website that will be available at ion.org. And the full paper is available for download for free. You do need to sign in with a free account, but you do not need to be a member to access the full technical paper. So you can go to our publication search archive, and you will find that under our listing for navigation journal papers. But again, thank you for your time and for attending today.